Hi everyone, and welcome to the first of our daily revision boosters. So what we're going to be doing in these is just going through a topic from biology, a topic from chemistry, and a topic from physics that's hopefully going to help you prepare for any of these little in-class assessment things that are coming up after the Easter break. One of the things that you do need to know are some of these physics equations that we've been looking at over the past 3 years. So the first one you're going to have to know for the assessments we'll be sitting in class is this one here. Charge flow is the current times time. So make sure you learn that, stick it on a flashcard, and then memorize those for me. So charge flow is current times time. Today's biology blast is looking at a couple of those key cycles we need to know. We're going to have a look at the water cycle and the carbon cycle. First up, we have the water cycle, which is this lovely diagram you can see in front of us. Now, the water cycle, as the name suggests, is how water is cycled through the environment. And what we need to know then are a few key processes. If we start up in the top corner here, so we're going to start in the clouds up here, then what we've actually got as the first thing that's going to happen is the process of precipitation. Now, precipitation is basically rainfall or snow, some kind of moisture falling as droplets. So we have precipitation, which happens because the water droplets get heavier and then they fall to the ground. Once they hit the ground, then we will see some element of percolation, which is where water trickles through the gaps in soil and rocks, or it's actually going to be taken up by our plants. So do remember that it's not all just going to end up going all the way down to oceans, as you can see in that diagram there. Some of it that ends up in the ground is then taken up by plants. So from that percolation, really two things that are going to happen. Either it ends up in the water systems or it gets taken up by plants. You can see there's a small element there that has surface runoff. That's the bit that doesn't actually percolate through the gaps. It just runs off the surface into rivers, lakes, the ocean, whatever it may be. For the bits that are taken up by plants, our next process we have is transpiration. Hopefully is familiar from some of our early biology work in B2, which is the loss of water vapour from the aerial parts of the plant or from the leaves. So what we see there is once the plants have taken up water, it travels through the xylem up to the leaves where it's then lost as water vapour. If we end up in the oceans, then we have evaporation taking place. So the sun is going to heat up the surface, and as a result of that, water changes from liquid into water vapour, the gas form, and then it will rise up. So basically transpiration and evaporation both generate water vapour. As the water vapour rises, we have the process of condensation occurring, which is just as that warm air rises, it then cools, and then because we're cooling, the water vapour condenses back into the liquid water droplets, and that's where our clouds come from. Those clouds are then going to cool and travel, and then eventually we get back to our beginning with precipitation. So what we've actually got there then are really 5 key processes to remember: precipitation, percolation, transpiration, evaporation, and condensation. So precipitation, rainfall; percolation, trickling through rocks; transpiration, loss of water vapour from the aerial parts of a plant; evaporation, surface water evaporating into the air; and condensation, clouds forming, is the simplest way to think about it. So make sure you know all of those processes and the overview of what that diagram looks like, because they could ask you on a question to identify which bit of the diagram has one of those key terms. The second process, the carbon cycle. This again is how we cycle carbon through the environment. Now what we have here is another little diagram at the bottom to give us the key points once more. So if we look, we're going to start off with carbon dioxide in the atmosphere. Please note it is carbon dioxide in the atmosphere. Do not just write carbon in the atmosphere, because if it was just carbon in the atmosphere, then we just have these small black particles up there. We don't. We have this colourless gas, which is carbon dioxide. So carbon dioxide in the atmosphere first of all. You will notice there is a single arrow, this one right here, that goes away from the atmosphere. So there is a single process that will take carbon dioxide from the atmosphere, and that is photosynthesis. So photosynthesis is that process that occurs within our plants whereby carbon dioxide and water are then converted into glucose and oxygen. So that means we're removing carbon dioxide from the atmosphere in photosynthesis. The only one that does that. Then we've got 3 arrows, this one, and this one, that are all showing respiration. Now respiration, if you're thinking about word or balance symbol equations, is the opposite of photosynthesis. This is where glucose and oxygen are going to create carbon dioxide and water. And all living things respire. So the plants, the animals, the bacteria, whatever it may be, they all carry out respiration, which returns carbon dioxide to the atmosphere. The next process we've got, it's on the side here, and you can see it's written as burning fossil fuels, but we can also refer to that as combustion if we're using real scientific terms. So combustion again releases carbon dioxide into the atmosphere. Then we've got a couple of other processes we need to be aware of. First of all, when our plants have carried out photosynthesis, we can see there's this little arrow here that is the plants being eaten by animals. So when plants photosynthesize, they make glucose. That glucose gets converted into things like starch, into cellulose. Basically, it's used to make biomass in the plant. When animals then eat those plants, the biomass is transferred from the plants to the animals, and it becomes part of the animal's biomass. Do not say that carbon dioxide is passed from the plants to the animals. It's not. It's carbon compounds. With both our plants and animals, you can see we do have another process here, which is decomposition. So basically living things die, and when they do, they decompose. And because of that decomposition carried out by bacteria and fungi, then they will also be carrying out respiration at that time, which releases carbon dioxide to the atmosphere. Alternatively, when things have died, they can, over millions of years, become fossil fuels. So the fossil fuels, hopefully we remember, are coal, oil and natural gas. They will then be burnt through the process of combustion in various factories, in cars, etc., which then releases the carbon dioxide back to the atmosphere. So that is the overview of the carbon cycle. Here's our summary. 3 processes that are going to release carbon dioxide to the atmosphere: respiration, decomposition, combustion. One process is going to remove carbon dioxide from the atmosphere: photosynthesis. It is worth remembering that when we talk about carbon dioxide, it's not a static line. We will find that the amount of carbon dioxide varies throughout the 24-hour period of a single day, because photosynthesis can only happen during the daytime, because it requires light. That means carbon dioxide is only removed from the atmosphere during the day. But respiration, the process that happens in all living things, can take place 24 hours a day. It doesn't need sunlight, so it happens all the time. So that means we get these little spikes. If you look at the graph in the bottom left corner, then you can see we've got these little spikes and troughs. That's just representing day and night, day and night, day and night. It's going to obviously peak during the night because that's when no photosynthesis is occurring, and it drops that little bit in the day when photosynthesis is occurring. But we can see that there is this general increasing trend here of the level of carbon dioxide in the atmosphere, and that is accountable to us as humans. Every time we burn fossil fuels, etc., that is going to increase the amount of carbon dioxide in the atmosphere. Quick reminder of our daily formula for today. Charge flow in coulombs is the current in amps times time in seconds. Today's chemistry check, we're looking at atom economy. Now, atom economy, quite simply, is the measure of how many atoms from our reactants actually end up in the desired product, the thing we wanted to make. So it's a value, and it's going to be between 0 and 100. If it's a low atom economy, so somewhere in the lower range of those values, then that tells us only a small number of atoms from the reactants ended up in the product we intended to make. If it's a high atom economy, then that means that lots of the atoms in the reactants ended up in our desired product. In any chemical process, we want a high atom economy because that means we are using the vast majority of the reactants to make the product we intended to make. The formula we need to know is this, and they're not going to give this to you on the exam necessarily. So this is one to learn. Again, flashcard it, learn it. Atom economy is the sum of the relative formula masses of the desired product divided by the sum of the relative formula mass of all products, and because it's a percentage, we then multiply by 100 to get it as such. So, sum of the relative formula mass of your desired product divided by the sum of the relative formula mass of all of the products times 100. Let's look at an example then. So, when we get a question on calculation, the first thing we do is, as we read it, we're going to highlight, underline or circle the key bits of information for us. So here we go, we're going to be looking at making hydrogen in this case. So hydrogen can be produced by reacting methane with steam. We've got our balanced symbol equation in the middle there. Calculate the atom economy for the process. So we're calculating atom economy, giving your answer to 3 significant figures. Do note if they're asking you to give a certain number of decimal places or significant figures, because that will be 1 mark in a question. So when we're doing this, the first thing to remember is, look at the formula at the top. Desired product divided by all products. We are purely looking at the right-hand side of that equation. The left-hand side, it's irrelevant. We don't really care what's happening there at all. It's all about the right. So, first thing we need to do is we've got to work out our relative formula mass of the desired product, which is hydrogen. So hydrogen, hopefully we remember on the periodic table, has a relative atomic mass of 1. Therefore, hydrogen H2, so that is going to be 2 times 1, which is 2. And we've got 3 moles of it. So we need to times that by 3, which gives us 6. We then need to work out the MR, so that's our hydrogen, sorry, of our other product, carbon monoxide. Now carbon is a mass of 12 and oxygen is 16. Remember, you've got a periodic table in the exam, so just look it up on there. So if we've got 1 carbon, then that's 12, 1 oxygen plus 16, that gives us 28. So that's our first bit. Even if you can't remember anything else, that is usually a mark for you for working out the relative formula masses of the 2 products individually. Next thing we need to do is we're going to substitute into our equation. So the sum of the relative formula mass of the desired product, which is our hydrogen, so that's 6, divided by the sum of all products. So we've got carbon monoxide plus our hydrogen, so 28 plus 6 goes underneath there. And then remember, because it's a percentage, we times by 100. So all we're going to do then is using a calculator, because do remember, we can always use a calculator. We just type it in, we get our answer, and on the calculator I get that as 17.647 and lots of other numbers then. Now we need to give it to 3 significant figures, so that's not the end. We then have 1 is our first significant figure, 7 second significant figure, and then the 6 would be our third significant figure. Because it's a 4 as the next one, obviously it's less than 5, we don't need to round up. and that will be 8%. And that's it. That's our atom economy. Quick reminder before we move on, our daily formula for today is charge flow. So charge flow in coulombs is the current in amps times time in seconds. In our physics prep for today, we're going to be looking at specific heat capacity. This is the experiment you love to hate. When we talk about specific heat capacity, we are referring to the amount of energy needed to raise the temperature of 1 kilogram of material by 1 degree Kelvin. This is the experiment. We did look at it in class. It's a long time ago. We may have forgotten. So here is a lovely picture to remind you of it. We've also got the basic method on the right there. This is one of those assessed practicals, so they can ask you how to do this, how to improve it, what the problems of it are, etc. What we actually have then is we've got a beaker with some water, and then it's got a thermometer and a heater in it, as we can see in the picture on the left. Now in this case we've got insulation all around it because this is set up properly. Now, the way that we actually do the experiment. We are going to place water of a known volume in our beaker first of all. We record the mass of the water because we need to know mass to calculate specific heat capacity. We then record the initial temperature of the water using our thermometer. We then turn on our heater for a fixed period of time, because if we know the time, then using other information from our heater, we can calculate energy as well. And then once we've done that, we turn the heater off, we record the final temperature of the water, and then because we've got the final temperature and the initial temperature, we can do a temperature change. Just final minus initial gives us the temperature change. So that's the basic method we need to know. Before we jump on to the calculation, do remember that they can ask you to suggest problems with a method they give you. So when it comes to spotting problems in a method, go back to the basics. Look at, are volumes the same? Is the equipment the same if you're obviously doing more than one experiment? Look and see what the differences are first of all, because if they're not the same, obviously we're not controlling all variables. Therefore, it's a problem. If it asks you about improvements, then think about ways that we could make it better. So if you've identified a problem that, I don't know, the beakers were a different size to one another, then obviously sit there and say the way we could make it better is use the same size beaker each time. If it was that one had insulation around it and another one didn't, then sit there and say make sure they both have insulation around them. Just generally speaking, we should have insulation around these experiments when we're doing specific heat capacity to reduce the transfers to the surroundings anyway. So just look for bits like that to help you out. Now, our calculation for specific heat capacity will have a question like this. And as always, it's a calculation. That means as we read it, we underline, highlight or circle the key bits of information as we go. So calculate the energy you need to transfer to boil 500 grams of water with a starting temperature of 20 degrees Celsius. Specific heat capacity for water is 4,200 joules per kilogram degree Kelvin. Now, you don't have to memorize the formula for specific heat capacity. That is given to you on the actual formula sheet for any physics paper. First thing we're going to do though is we need to work out the temperature change. So our temperature change, in this case, we start at 20 degrees and we're going to boil water. They're assuming you know that water boils at 100 degrees Celsius. So 100 minus 20 gives us a temperature change of 80 degrees C. We also need to know the mass. Now in the question here, they've tried to catch us out because the mass is in grams. The standard units for mass in physics is kilograms, folks. So what we need to do is 500 divided by 1000, and that gives us 0.5 kilograms. So we've got a temperature change, we've got the mass, and in the question they've given us the specific heat capacity. On your formula sheet, it will tell you that energy is mass times specific heat capacity times the temperature change. All we then need to do, substitute in our values. Mass was 0.5 kilograms, specific heat capacity 4,200, and our temperature change is 80. So again, grab a calculator at this point and we'll do 0.5 times 4,200 times 80, and that gives us an answer of 168,000. And because it's energy, will be in joules. And that's it. Don't forget to come back again tomorrow. We'll be looking at another 3 topics to help you get prepared for these upcoming assessments.